Hello, welcome to my channel. Today we're going to study forces. So, what is a force? The basic definition of force as we know it in a common language is it is a push or a pull. Okay? So, if you apply push or pull, you can accelerate a body or an object. Okay, so the very basic definition of forces, it can be a push or a pull. Oops. So let me write here. It can be a push or a pull. Okay, and it is a vector quantity. So usually, if we're dealing with vectors, we can represent vector as an arrow with the arrow tip as the direction and the length of the arrow as the magnitude of that vector. So when we say that this vector is, say, 2 newtons, and don't forget that the arrow, 2 newton, and then let's say you have a 4 newton vector force, so perhaps you can just double the length of this force. 1, 2, something like that. So this is just an approximate value. So let's say 4 newton. As you can see, a vector quantity, you have for longer arrow, it means the vector has a higher magnitude. But for shorter arrow length, it means the vector quantity has a lower magnitude. Okay, so how do we add forces? As you remember, force is a vector quantity. So when we add forces, we have to consider both the x and y components, and perhaps you can do the 3 methods, the component method, and the graphical methods such as polygon or tip to tail method, and the other one is parallelogram method. So for example, you have two vectors here. Let's say we have vector A and then vector B, and then what you can do is this one is a parallelogram method. We can draw a parallelogram here. Okay, so what you can do is draw a parallel line with respect to one vector, let's say vector A or vector B, and another parallel line with respect to another vector, in this case, vector B. And then the resultant is that straight line from the origin to the tip of, or to the diagonal of your parallelogram. So let me draw that, something like this. Okay, and of course, the resultant is a vector, so you need to you need to draw the arrow as an arrow. So this is your resultant, which is just A plus vector B. Okay, so this is for 2D. What if you have a simple vector addition? So let's say you add, let me draw it here. Let's say you have another vector here. Let's say one vector is going to the right, something like this. And let's say another vector, let me use a different color. Let's say another vector, let's say to the left. And then let's say we have another vector, let's say again to the left, something like this. Should be close to the other. Better if it's a straight line. So something like that. So just remember these are two vectors. So the first the blue vector, let's just call it, or let's just have an arbitrary value. Let's say 35 Newton. And then the green vector, let's say 20 Newton, perhaps. And of course, the white vector, let's say 35 Newton. Now, how are you going to add this? These are vector quantities, so you need to consider the direction. You need to consider whether it is positive to the right usually, or to the positive x-axis, negative to the left or to the negative x-axis. So you can add the vector summation of f, meaning you add all the vectors. That should be equal to if you are going to add 35, it's to the left, so you put negative sign now. Negative 35 Newton. The other one is also negative to the left, which is negative 20 Newton. And the other one, the white vector, color white, is 35 Newton. It is to the right, so we can assume it's positive 35 Newton. So if you're just going to add them, you should get an answer of, I think you don't need a calculator for this. If you have negative 35 and then you have another 35, so you can just cancel out the 35 value. So this will just cancel out. So what you will have is negative 20 Newton, or it's negative 20. So, or you can say, or to the negative x-axis, or you can say 20 Newton west, so something like that, or 20 Newton west. Okay? Now let us discuss what are the different types of forces. So forces can be categorized as either contact force or non-contact forces. Can you imagine that? There is what we call non-contact forces or action at a distance forces, meaning you can apply a force even if you're not touching them. Amazing, right? Just like in sci-fi movies, like Magneto can control magnets or metals, electric forces. Okay, so let's start with contact. Okay, so for contact forces, the very basic types of contact forces, as I've said earlier, there is push or pull. But when you're pushing or pulling something, you need to touch that. Okay, so if I push you, I have to touch you, or I pull you, I have to touch you. Okay, so there is physical contact. So let's have examples of contact forces. Of course, the first one, you can say push. So you apply a force, something like that. Then the object can move or can just stay at rest. And then you have another type of force, pull. So you put it, or you apply a force, physical contact towards you. So it's pulling. You apply a force. What else? What else can you think of forces that requires physical contact? How about, what is this? It's called friction, right? So one example of contact force is friction. Later we will discuss the different types of friction. But friction is a force on surfaces in contact with each other. So let's say you have a book here, something like that. So let's say this is your physics book, or never mind the name of the book. And let's say you apply a pushing or force. Sorry about my hand, doesn't look like a hand, but anyway. Now it's on the surface, okay? You might not see it, but actually there are contact points, okay? And that contact points prevents the object from moving, smoothly. So it opposes the force that you apply to the object on the surface, or let's say on the table. So that is friction. It requires contact. You cannot have friction if you don't have contact, okay? So let's discuss friction later on. How about other examples of contact forces? What is this? I can experience this force from the tip of my finger to the joints here, to the tendons, to the wrist, this, and even to the elbow. It is the force applied in any connecting objects. It starts with letter T. What is that? It's called tension. Okay, tension is the force applied on connected objects. Like let's say you have a string, so let's say these are connected. So sometimes if you apply a tension or a force here, that is transmitted also to other parts of the connected part of that object. Okay, so there's tension also on the other side. Okay, so we now have push, pull, friction, and tension. What else? I am holding a book. And of course, the book has weight. So I am supporting the weight of that book, right? I am supporting it. I am applying a force upward to counteract the weight of this book. If there's no supporting force, then the book will fall. So there must be something. What is that? It starts with letter N. That is your normal force. Or sometimes we call it support force. Support force. Okay? So it's usually perpendicular to the surface. So let us draw something here. Let's say you have a table, something like that. Oops, doesn't look nice. But anyway, and then the table has some legs, something like that. Okay, and then you have a book here. Okay, I'm not good in drawing, but anyway, so you have a book, and the book has a weight, of course. The weight is always downward. Okay, so let me draw that. This is your weight. Again, the book doesn't fall because of the table. It's which supports the weight of that book. So there must be another force that is applied, and the direction of force is upward. So that is what we call the normal force, or we can just write a symbol Fn. Okay? So sometimes you will encounter these types of problem, like in an inclined plane, something like that. And then you have a block of wood sliding. There is friction as it slides downward. Of course, that object has a weight W. The normal force, if the surface is inclined, is still perpendicular. So the normal force here is something like this, perpendicular to the surface. Okay, so let me write here, that's perpendicular. Okay, so this is now your normal force. It's a little bit slanted as well because the surface is also inclined or slanted. Okay, do you know other contact forces? Uh, what else can you think? How about perhaps air resistance can be considered a contact force, right? Because it is directly applied by the air. So let's say you're parachuting and then something like that. Point, point, point. Yeah, you're parachuting. And then you have a weight, of course, the total weight. And then there is something that's supporting it, decreasing the speed as it goes down. So yeah, perhaps you can call it force of air resistance. So air resists the motion of your parachute. In this case, it looks like umbrella, but I don't know. It's a parachute, guys. Believe, yeah. Okay. So it might be related also to a force inside a fluid. Well, a fluid is a gas or liquid. So perhaps there are some relations on that of what we call the buoyant force. Let's call it FB, not Facebook, but buoyant force. How do you spell it? Buoyant. I think it's B-O-U, buoyant force. Okay, so these are examples of our contact forces. Now let's proceed to non-contact forces. Oh wait, perhaps we can discuss further friction. Okay, let's discuss friction next. Okay, so for friction, let's say you have a ref. You're pulling the ref. Okay, I have a ref here. I can pull it. Yeah. As I apply the force on the ref, there is something that opposes my force, and that is what we call static friction. There is something that opposes the force that I apply, but the ref is still stationary. So that force, we call that force that opposes the applied force static friction, in general friction, but if the object is still at rest, it's called static. But when you start moving the refrigerator, it's a little bit lighter now, but there is still a force that opposes the applied force. That is now what we call kinetic friction, an opposing force parallel to the surface when the object is already moving. Okay, so you have friction, we have static and kinetic friction. So let's draw our diagram for the refrigerator. Okay. Okay, so this is your ref. Now you apply a force. Let's just draw it something like this. You apply a force like that. Let's call it F. And now the ref is still at rest. There's already an opposing force. We call that force, what do you call it again? Static friction, Fs, static friction. Okay, and now it is moving. It's moving now. You are still applying the force. So there's a force in that direction. There is still a force, even if it's moving already. There is still a force opposing your applied force. Let's just draw it. What do we call that force? Opposing your applied force parallel to the surface. We call that static, kinetic friction. We'll just use a symbol Fk. Okay? So when the ref or the object is still at rest, we call it Fs, which stands for static friction. Now when the object is moving, we call it kinetic friction. The units of these frictions is the same, Newton. Okay, so again, for static, no movement. For kinetic, it is now moving, or there is motion. Okay, so if you are going to graph these forces, the friction, let's graph it, something like this. Okay, you are applying a force, so the friction is, when you apply the force, you keep on increasing the force, the friction seems to increase as well. Okay, so let's say this is the friction, the graph of the friction versus time. So as you apply the force, the friction tend to increase as well. So it is increasing until such time, if you apply too much force, and then there's a point wherein the object will start moving. Okay, when you reach that maximum kinetic friction, that maximum force. So the graph will look like this. The friction keeps higher and higher, and then smaller. But there's still friction when the object is already moving. So we call this part, we call this part, let me increase that. We call this part static friction. We call this part when the object is already moving, kinetic friction. And there's a maximum here. That's the limit, whether the object will move or not. It's the highest. So we call it F, still static, Fs max. Okay, Fs max, maximum static friction. And I will just give you the formula for the static friction. The maximum static friction is given by this formula. Fs max is equal to a constant. There's no other factor but that factor between the two surfaces. Okay? So in this case, the tiles, the floor, and the ref, the bottom part of the ref. So, and that constant, there are values for that. Mu s, or the coefficient of static friction, okay, times the normal force. What is the normal force? It's a support force. It's usually perpendicular to the surface. Remember, the the refrigerator has a weight, so it's downward. Now, the normal force is upward, which is the force applied by the ground. So we call it Fn. Okay? So as you can see, Fn is somehow related to weight. So if you know the weight, you can easily determine the normal force. It's usually equal because it's perpendicular, so equal in magnitude but opposite in direction. So the formula for the static friction, maximum static friction is mu s Fn. What again is mu s? Mu s is the coefficient of static friction. Okay. How about for mu k? The kinetic friction is given by this formula, mu k times Fn. Similar but different constant. Okay? Just remember that you have a static friction, it goes from 0 to the maximum. So there's this value for the static friction. It's usually from 0 to maximum static friction, Fs max. Whatever the value for this, you can determine that. So it's usually lower, but when you exceed that maximum static friction, after that, the object starts to move. So as you can see here, the maximum static friction is the highest friction. It's called max, right? And if you apply it in real life, you need to exceed that. Like if you're pushing the car, it's hard to make it start, right? But when it starts moving, it's easier. So don't stop. When you make it, when it starts moving, don't stop because you have to exceed that maximum static friction again. Okay? So now let's discuss non-contact forces or action at a distance forces. Okay, so let's start with the first, also very common, non-contact forces or force, also called action at a distance force. The first and the most common is the gravity. Like all of us, we are all experiencing this. We are attracted towards the center of the earth. Everything falls, right? So that is gravity, and everything that has mass has gravity. But if you're talking about very huge mass object or like stars, planets, they have tremendous amount of mass. So they have more or higher gravitational pull. Okay, so this is planet Earth. Even if you jump, joink, 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 we are all attracted towards the center of the Earth. And wherever you are, you jump, you're still attracted towards the center of the Earth. Even if you're flying, the airplane will want to go this way, again, it will fall downward towards the center of the Earth. And Earth is pretty big as compared to other asteroid comet. So we can attract moon. The moon is attracted to us. And the sun is much bigger. Sun. So we are attracted towards the sun. There's a pull of gravity. So we are now circling around the sun. So that's a very common example of action at a distance or non-contact forces, gravity. The next example is electric force. So we know that positive charge, what will happen? Are they going to be attracted or repelled? So if you have both positive charge, there will be a repulsive force. They don't want to be with each other. They're same charge. So the force will be repulsive. So they want to move away from each other. Now, what if you have, let's say, positive and negative? Now, unlike charges will attract each other. Positive, negative, attractive force. Okay? So something like that. This is the very basic way the very basic way to explain the action potential in the cell membrane. If you're biology or health related majors, psychology, um, you're studying the parts of the cell membrane in your anatomy and physiology courses. Now, if you're going to study the electricity in the cell membrane, it's actually caused by the different polarity or different charges. So let me draw it. So let's say this is your cell membrane. Okay, this is positive, positive. Let's say that part, let's say the outer part of your cell has a lot of ions, positive ions, let's say positive ions. And then in the inside part of your cell, let's say you have a lot of negative here. Now there's an attractive force. Okay, the force is attractive because one part is highly positive and the other part is highly negative. Okay, so what will happen? If that is too much, or if there's a way for them to go inside, they will want to be with the negative charge. So there's like electricity, okay, because they're attracted. There's a force between the two charges. So that electricity, usually in millivolts, is what we call action potential. It's in units of millivolts. Okay, another, I would say, common example, and I think all of us have seen it, have heard it, thunder, right? So sometimes, let's say these are your clouds, something like that, that's a cloud. And then sometimes because of friction, you've experienced that, right? Because of friction, you're generating charges. So let's say our clouds are now highly negative, okay? And then it has to be discharged. It will be attracted to the positive charge. Let's say this is your positive, the ground is positive, or whoever is closest to that, and the trees higher or structures that are taller than the ground, definitely, the electricity will travel, will be attracted towards that closest object with positive charge. So now you will have thunder, lightning, something like that. Okay, so there will be thunder. That's the physics of lightning because of charges. You've seen it. Perhaps I can demonstrate it. Let me use my camera here. Okay, so let me use, let's say I have bits of paper here. Okay, I hope this demonstration will work. So let's say I have a comb, and because of friction, some of the electrons will go to the surface. My hair is a little bit messy now. My hair is a bit dry. So if it's not dry, it's a little bit wet. So it's not that efficient. So if I am producing some friction here, the electrons will go to the surface of the comb. I just destroyed my hairstyle, guys. So now I have a lot of electrons, and then it needs positive. So look at my bits of paper, the closest. Whoop, whoop, whoops. It is attracted. So that's an attractive force. Amazing, right? Okay, let me do it for my silky clothing. I hope it will work more. Look at this. Ooh, it is attracted. Oh, another one. Oops, it's even stronger. Okay, so that's your electric force. Okay, let's now discuss another type of non-contact force, the magnetic force. Should be amazing. Okay, so it's the force between magnetic materials. So let's say you have, let me draw it. Let's say you have a bar magnet here, another bar magnet here, bar magnet, And then let's say this is North Pole, and then South Pole, and then South Pole of the bar magnet. What will happen? Are they going to be attracted or repelled by each other? Again, it's similar to electric forces. If you have same polarity, north-north, they will be repelled. They don't want to be with each other, so they will move away from each other. But if, oops, these are also south-south, so it will be repulsive. Okay, let me have you. How about for opposite charges? Okay, so let's say this is your North Pole and this is your South Pole. So now they will be attracted towards each other. Okay, I think I can demonstrate it. I have a thermos bottle here. I think this one is north. Let's say this one is north and this is south. Let's say this is south and this is north and this is south. If I point the north parts or south part, same south part, same polarity, they should be repelled by each other. Okay? But if I point the north part, which is opposite polarity, they should be attracted. So let me point the south-south. So let me show it here. Okay. I don't know if you can see my video here. Okay. Something is blocking. So I have here a magnet. I will point south-south, south pole to south pole. This should be repelled. Look at that. Woo! It's moving. I'm like Magneto, guys. Non-contact forces. What if I point the north part? So north-south attracted towards each other. Look at that. Far away, but look at that. Amazing, right? So they're attracted towards each other. That's your magnetic force. Another non-contact forces. Okay? Okay, now let's discuss the two remaining non-contact forces. So let's start with the strong nuclear force. So the strong nuclear force, sorry for my hair. From the word itself, it's the force that binds the nucleus. Okay? So what's inside the nucleus of every atom? So let's say this is your nucleus. And of course, you have the electrons around the nucleus. And inside the nucleus, you have the proton, positive charge, proton, positive, and you have the neutron, no charge. But they seem to be binded, you know. And you know that force is the strongest force. Although it's a very, very short distance, but still non-contact. They're binded by that very strong nuclear force. Okay? And with that force, there is stored energy. That's why we can harness nuclear energy out of it, right? Okay? So the other type of force is what we call the weak nuclear force. It's basically the force of radioactive decay. Okay? So radioactive materials, so let's say they're radioactive, they're emitting radiation. This is radioactive. They seem to eject excess amount of energy. Okay, and usually they decay into beta decay. So it's the force of radioactive decay. We will discuss this in detail if we have for our topic on nuclear, introduction to nuclear physics and also medical physics. So these are your non-contact forces. You have gravity, you have electric force, you have magnetic force, and you have strong and weak nuclear forces. So Forces can be categorized as well as either fundamental or non-fundamental forces. Fundamental forces are very basic. It's always present. You can always expect that to be there. And non-fundamental is only present in certain conditions. If there's, for example, tension in connecting objects, friction, normal force, support force. So fundamental forces, the first one, of course, is your oops, gravitational force. Gravitational force. The other one is your strong nuclear. And you have also the electroweak nuclear or electroweak force. And the other one, of course, the electric and magnetic. You can combine it as electromagnetic force. Okay, so these are your fundamental forces. For non-fundamental forces, you can have examples such as tension. Usually we use a symbol T. You have friction, frictional forces, small f. And you have the normal or support forces, normal force, F. Usually we use the symbol Fn. Okay? Now let's focus on the very common, we experience it, non-contact forces, and that is your force of gravity. So, you know, anywhere you are standing on surface of planet Earth, whether you are here, you jump, you are always attracted towards the center of the Earth. The gravitational force is basically the force that is applied by planet Earth on our body, on us. So that's why we have weight. So we call it weight, right? The unit is in Newton. Okay? And wherever you are, even if you're standing here in the South Pole, you're always attracted towards the center of the Earth. And weight is equal to mass times the G. Now, in planet Earth, the acceleration due to gravity is 9.8 meter per second squared. Now, this gravitational force depends on the size of the object, or not the size, but the mass of the object. So we can also consider moon. So moon has gravity as well. So let's say you are standing in moon, okay? You will experience their gravity. The gravity in moon, if I'm not mistaken, is about 1.6 meter per second squared. Okay, so that's a gravity in moon. So your weight in moon is a little bit lighter. Okay, so it's a little bit lighter in moon. Okay, so, and of course, moon and Earth are attracted towards each other because of their tremendous amount of masses. Okay, so we define weight as the weight is the gravitational force exerted by Earth. Gravitational force exerted by our planet, by Earth. Okay? And what is mass? So we have here M. Mass is the amount of matter. Amount of matter contained in an object. Okay? And of course, the unit for weight is Newton. The unit for mass is kilogram. Sometimes we are all in planet Earth. Sometimes we use this interchangeably, but in a scientific language, weight is Newton, okay, while mass is kilogram. That's as a unit for mass. So again, the difference between the two, between mass, so mass is something constant. Okay, it is a constant quantity. And then you have weight. So weight can depend on location. Depends on your location. So at the surface of planet Earth, it's fairly, your weight is fairly the same because the acceleration due to gravity in Earth is 9.8 meter per second squared. Let's say now this time, let's say Mars's acceleration due to gravity of about 3.2 meter per second squared. So the acceleration due to gravity in Earth is approximately three times higher than the G in Mars. So what does it mean? So it means everything there, if you jump or it's a little bit slower. The acceleration is a little bit slower. So if you are in Mars, in Earth, perhaps you can jump high enough. But in Mars, imagine you can jump, say, about three times. At least three times you can jump higher. Imagine we're like superhero in Mars. But of course, because of spacesuit, it will also be heavier in Mars. We have to wear spacesuit. So in Earth, perhaps you can jump, okay, I can jump chung, chung, without injury. But in Mars, you can jump perhaps second floor. Okay, I'm okay, I'm not injured. Because acceleration due to gravity in Mars is lower, your weight is lower, you're lighter in Mars or in Moon. That's why when you see those movies or documentaries, videos on Moon, they're like they step, but it seems like they're jumping because definitely we are more powerful there because of our weight is lighter. Okay, so now let's end this topic with Newton's law of universal gravitation. Why do we have gravity? So according to Newton, every particle in the universe exerts an attractive force on every other particle. It means every mass, I have gravity. Okay? Your seatmate, your crush, you're sitting beside your crush, you have gravity, the force of attraction. But I think it's very, very small that it's almost not non-existent. Okay? A particle is a piece of matter small enough in size to be regarded as a mathematical point. The force that each exerts on the other is directed along the line joining the particles. It's that line towards each other. Okay, so let's end this topic on forces. See you in the next topic on the next topic would be Newton's laws of motion. Okay, enjoy learning physics, guys. Choose. Bye bye.